Hello and welcome back to Calculus 1, section 2.3 on computing limits. We are going to take a look at few different methods of computing limits by analytical methods, which means calculations and algebra. The first lesson on Intro to Limits was a numerical approach where we calculated the values and then infer what the value of the limit was. And also we looked at the graph. Today we are focusing on, well, the three sections we're going to cover, hopefully. The first section is going to be on computing limits using algebra. Then we move into computing limits, the infinite limits, and then finally limits at infinity. So those are the three in a row. The first order of business is to say that there are a few ways to compute the limits. Okay, let's go. Ways to compute limits. And number one, if you have access to graph and the graph is clear, and especially if you have infinities and so on, graph is something that, sometimes can give you the answer quickly and efficiently without you computing anything. The way that works 100% of the time, so if you don't want to learn, let's say you don't want to learn anything in this chapter at all, apart from limits are fancy way to compute the y value, and you are supposed to compute the numerical value of the limit, the only thing that works 100% of the time is that numerical chart approach, the table of values that I had last time. Remember when we computed values and we said, oh, from this side is 9, from this side is 9, so it's 9, right? So chart / table of values, whatever you want to call it, is the method that is the one that you can, just like graphing, guys, you learned what the parabola looks like and a square root looks like, an absolute value. You learned and memorized all of these shapes through your algebra and pre-calculus courses. But do you really need to know all of that stuff? Yeah, for convenience, but what can you do every time? Pick x's, compute y's, connect the dots, like in a coloring book, right? It's that simple. You don't have to learn any shape of any function ever, right? Because when x is 3, you compute the y value. When x is 4, you compute the y value. And you just have a set of these points that you plot, and you just snake the line through those points. It works for every single function that exists, even those that you haven't learned yet, right? But then for convenience, you learn, okay, this is what x squared looks like, this is what straight line is, and so on. And then it's faster than computing, 10 points and connecting them. So in the same sense for limits, we are going to now learn number 3 and number 4 and number 5 and so on. But the only one that actually works 100% of the time, and you can ignore the rest of the chapter completely, is if you are willing to waste time computing each point individually. So I'm going to list as the most dangerous one on number 3, which is plug-in. And then we are going to move into the next one, which is going to be called algebra. And then we're going to have those infinities, and we'll see which way infinities work. So now, I'm going to give you that these two are in 2.2, these two are in 2.3, and this one is 2.4 and 2.5, right? So that's your, in terms of sections for the chapter. The goal of today is to cover those 3, 4, and 5 points in 3 different sections. The first order of business is to say, the plug-in method. It's not called that way, that's my subtitle. Recall that we said that limits compute the y value of the function. So the limit of x squared as x goes to 3, we calculated using graph and a chart last class that it's 9. Well, you get the same answer if you plug in 3 squared is 9. But we said that the limits don't work by plugging in. But then they gave you the same answer. So here are the few things that you have to be very, very careful about. Anytime when you want to compute the limit quickly, and you plug in the value inside the formula, and you get some kind of answer, if that answer is just like this, 9 and you're done, actually it's okay to use that method. For instance, you have a limit x approaches 4 for 2x minus 6. Well, you will just say 8 minus is 2 because you plug in 4. Okay, to plug in 4. That's okay, right? If you go and say, what is the limit of sine of x minus, let's say, pi over 4, as x approaches pi? It is okay to plug the limit here because you are going to get a numerical value for it. So you would say, okay, this works out to be sine of 3 pi over 4, which is negative root 2 over 2, and you're done, right? So that's also cool. And then you're going to run into a problem like this. Limit x approaches 5 for x divided by x minus 5. This is where it's no bueno to plug in value, because if you plug in value, you will get 0 in denominator, and that method then fails. So we cannot use plug-in method because denominator equals 0. So you have 3 examples where your answer is 9, and then 2, and then negative square root of 2 over 2. Anytime when you plug the value into the formula within the limit, and you get the numerical finite answer, you are good to go with that answer. On the other side, anytime you plug in a value and you get 0 in denominator or something weird happens, there are other situations as well, well, in that case, plug-in method doesn't work. You would have to use other means to calculate the limit. And we would like to learn about those. So plug-in method obviously is easy because you are technically repeating what you learned in pre-calculus and algebra. You plug in the value for x, you calculate the number, and you move on with your life. It's the algebra part where we need to pay attention. So let's say that you are looking for the limit of, let's say, x goes to 3 for x squared minus 9 over x minus 3. I'm going to write it in blood. Plug in method fails. You have 0 in denominator. If you plug in x equals 3, your denominator is 0 and you cannot compute. Now you might go and say, well, if the denominator is 0, the limit doesn't exist. No. You cannot claim non-existence of limit because the denominator is 0. And this is perfect example for that. What can we do?
You factor it.
Excellent. Factor the numerator into x minus 3, x plus 3, and you still have your denominator x minus 3. And hopefully you see algebra that x minus 3 cancels. So this problem is now equal to the limit x goes to 3 of x plus 3. And now if you plug in the value, you get 6. You see that? So our problem started with 0 in denominator, but the limit is still a finite number 6. This is why you are not allowed to plug in a value and talk about the existence or non-existence of a limit if denominator is 0. You have to massage this expression with algebra to get rid of that 0 in denominator. Sometimes it's possible, sometimes it's not possible to get rid of it. Here is an example where it's not possible. Say you have limit x goes to 2 of 3 divided by x minus 2. Whatever. All right? You are not able to factor, to cancel, to plug in. There is nothing that you can do in case, right, that we learned for this particular problem. Crying is allowed. And I do have tissues in my office, so, and the wide shoulder if anyone needs. I can accommodate up to 4 at one time, two per shoulder. Okay, that's for crying on limits. Okay, so 3 divided by x minus 2, x goes to 2. If you plug in x equals to 2, you get 3 divided by 0. Now, what is the way to solve this problem? Well, I just told you that none of the algebra would work. There is no factoring. There is nothing you can do. So, in this case, you will draw the graph because this is the 1 over x graph. Shifted, right? So that's a joke of a graph in comparison to, some of the complicated functions that you can get in mathematics. So this problem has to be solved either by looking at the graph or by doing the chart of values. So what I'm going to do is I'm going to say, no, y equals 1 over x looks like this, and then minus 2, shift right 2 units. Right, this is, you don't have to write this, at least this has to be running in your head. So you know that you have to draw 1 over 2, you have to draw 1 over x graph shifted right 2 units. So you will draw x and y coordinate system. Then you will draw vertical asymptote at 2.
It's not on the screen. It's on the screen.
What do you mean it's not on the screen? It's right there. Patience, young Padawan. All right. So we draw our function, and then we do Romeo and Juliet approach. Juliet, right, red from the left, she's going to get negative infinity. Romeo is going to get positive infinity. Because they don't match, we have the overall limit to be does not exist, right? So, again, Juliet approaches 2 from the left. Her answer is negative infinity. Romeo, on the other side, approaches number 2 from the right and is getting positive infinity. By the theorem we learned last time, approach from the left, approach from the right, they give you different answers. Limit does not exist. So, we would just say equals dne. So, in this example, denominator was 0, and you got does not exist. Previous example, denominator was 0, you got 6. So you cannot make that this, you cannot just put all of these limits in a bag and say, oh, denominator 0 does not exist. You try, obviously, to pull that off on a test. It's wrong every time. You have to check. And when I call this subtitle algebra, in that bag, you technically have the rationalizing if you have square roots. So I'm going to log in and take a look at some of the homework problems. So it's rationalizing, adding fractions, canceling after, no. Factoring, there we go. So rationalizing, factoring, then canceling, or maybe you have fractions that you have to add together or something like that. It's a finite bag of tricks of different things that you can get. Just depends on how many homework problems you practice to see the situations that you can run in. So I'm going to pick a few problems, and these are introductory problems where you see denominator is 0, you get the limit is 6. Another problem over here where algebra could not help you at all, and the limit was, in this case, does not exist because the left and the right. And we still had to summon the graph, right, and use it to calculate this. All right, so now, please. Good. It's my life. My life's biggest concern, guys, when I'm logging into this software to get the textbook, it doesn't ask me about the little puzzle where you have to pick the traffic signs or that one is so stressful. You have no idea. It's like pick all the pictures with the car on it, and then you have a picture. There's like 3 pixels of a car. It's like, do I click this one or not? Because you know instantly that if you miss on that one, it was obvious either way to click. You have to do it all over again for storefronts or traffic lights or something, and it's look. All right, so limits, techniques for computing limits, and we are going to take a look at some of these examples. I think they provide you with good amount of these exercises. Now, for whatever reason, my subscription to Edition 3 expired, so I'm using Edition 2, but problems are problems, so who cares? Let's take a look at one of these limits, what they have. So I'm not going to put the problem number because it doesn't match your version. Limit x goes to 3 for negative 5x divided by square root of 4x minus 3. The easiest method for taking limits is plug in. As long as your denominator is not 0 and you get the finite value, you should be good to go. So can we plug in? Yeah, we get negative 15 divided by square root of 12 minus 3 is 9. That's negative 15 divided by 3, negative 5. So limit is negative 5. And that was nice and easy. Yeah, this is the issue with this edition because it has just the cheap problems and then immediately goes into burning pits of hell without having anything in the medium range. Your edition, the edition 3, they said they added 17% of the medium spice problems, and I really have to. Oh, here's the nice one that it's kind of halfway here and there. It does have a Oh, okay. So limit x goes, not every limit goes to 3, but okay. So x squared minus 2x minus 3 divided by x minus 3. Can we plug in?
No.
No. So what is the hope now? Factor. Hopefully it will work out if you factor. All right, let's go. Don't forget to copy the limit in every step until you get to use it. Just like you copy plus for order of operation until you get to use addition, right? You get to copy limit every step until the last step when you use it up. What does this factor into? X minus 3x plus 1?
Yeah.
That's what I heard? Okay, good. Okay, great. So x minus 3 dies, and we get 4 as the answer. Well, that's nice. Limit, see, x goes to 9 now, so we can relax, of square root of x minus 3 divided by x minus 9. Any suggestions? Can we plug in?
Yeah.
We cannot plug in. Very good. No plugging in, because 9 minus 9 in the denominator is 0.
We have a difference of squares of the denominator, right?
Ooh, you know the trick. All right, so standard way to solve this problem is pain and misery, because you have to rationalize, right? You have a square root. That triggers rationalizing, which is you multiply by root x plus 3 divided by root x plus 3. Then you FOIL a whole bunch of stuff, and stuff will eventually cancel. And that is the standard way to solve the problem. But then Nicholas over here came up with the God tier, and that's going to be our second way to do the problem. So let's first do the standard way, because again, you see a square root, most likely rationalizing solves the problem. So standard way is to multiply by root x plus 3 divided by root x plus 3, and then work out the algebra and cancel stuff eventually. So limit x goes to 9. When we multiply, root x times root x gives us x. The middle terms will cancel. So that's negative 3 root x plus 3 root x. They cancel. And then you have minus 9. Now, in denominator, the trick is to leave them without multiplying, because when these middle terms cancel, you have, as you can see, you have x minus 9 in the numerator, and then you have x minus 9 that you did not multiply in denominator. So now when they cancel, you get the limit x goes to 9 of 1 over square root of x plus 3. Well, that's 1 over 6. That's 1 over 6. I should separate these problems. So this would be the standard way to do problems that contain square roots with limits by what we call rationalizing, right? Now, let's take a look at the God tier over here provided by Nicholas, right? Nicholas said, well, that's perfect squares, right? I don't see a square on x, but still, we can use square roots, right? And that's the trick. So What he suggested is, you know this formula, a squared minus b squared is a minus ba plus b. This is the formula that you learned as difference of squares in your algebra classes, right? Now, you can actually have a minus b, and you can factor that one into root a minus root b, root a plus root b. That's okay. So, when you have the same problem as above, limit x goes to 9, and then you have your, what do you have? X, root x minus 3 divided by x minus 9, you unleash this formula upon the denominator, right? And you get, that's a good one, limit x goes to 9, root x minus 3, and now when you factor the denominator, you get root x minus 3, root x plus 3. And then these guys cancel. So it's a one-step solution. Cool, huh? And you get 1 over 6 immediately out of this. So again, it's all about your algebra prep and your pre-calculus prep. So you can go and do rationalizing, or you can just quickly, if you see the factoring, you can factor there and be done. Fair? Good. It will come back. It's the same like bicycle, right? You fall so many times, everything hurts. All right. Problems that we are going to use later a lot involve particular equation from your pre-calculus 1 class called difference quotient. That is extremely important concept for calculus. We'll deal with that in chapter 3. Right now, we are learning to take the limit of the difference quotient. Now, if you do not remember difference quotient, here is the review for it. Difference quotient is equal to f of x plus age minus f of x divided by age. You learned this in section 1.7 in pre-calculus 1 course, which is probably a year ago. Maybe you had two homework problems, one lab exercise on it, and probably was not even on the test. It's one of the pillars of Calculus 1. So technically you did not go through pre-cal course. That was the point. All right, so what are the specs of this formula? We see two features, well, three features. We see an f of x, that's your standard function. Then you see f of x plus age, that's a function composition. And then you have divided by age, which is a parameter, which is the same as x plus age, the same age. So, if I want to create a difference quotient for, let's say, x squared plus 2x. So let's say f of x is equal x squared plus 2x. What's the difference quotient? DQ stands for difference quotient, not Dairy Queen. So, DQ. Let's go. You already, guys, I asked you to look at this as 3 building blocks. 1, 2, 3. 3 building blocks. F of x is a building block that you already have. So that one will just plug in there as a module, just like you dump it. I need to create a building block for f of x plus h. Well, this one tells me to replace every x of the equation with x plus h. So it's x plus h squared plus 2 times x plus h. And now we just need to work out algebra. So I replaced every x of the equation with x plus h. So now to work out this algebra, I have to another F word. Foil. We have to foil this one and then add these places. So we have x squared plus 2xh plus h squared plus 2x plus 2h. So when you foil everything and distribute the 2 for the second term, you have this long expression, and that gives you x squared. Actually, you can't add any of these. They all, yeah, there are no like terms. That's it. This long expression is what you have. So now you can compile difference quotient. dq is equal to, we'll have to have a longer line because the f of x plus h is this x squared plus 2xh plus plus h squared plus 2x plus 2h, and now minus original function in parentheses, that's x squared plus 2x. We'll have to distribute that minus later. And everything is divided by h. Technically, you're shoveling a lot of algebra here. Now you distribute this minus. So copy all of these terms in front. Plus 2x plus 2h minus x squared minus 2x divided by h. At this point, you see that x squared and x squared cancel, and then you have positive 2x and negative 2x. They cancel as well. And only the terms with h remain, which means that you can kick h out. You're left with 2x plus h plus 2 divided by h, and at this point h cancels and you are left with 2x plus h plus 2. So this is the full problem from pre-calculus 1 worked out. When I teach pre-calc 1, this problem is on the test. Because this particular calculation with the limit embedded, which is our next problem, this particular calculation is one of the pillars of calculus 1. It's called the derivative. Yeah. So it's very important to be able to do these calculations with difference quotient. Now, the difference quotient that they gave us in a textbook is not for the quadratic function, it's for rational function. So that means that we would have to shovel fractions here. But that's okay, we'll live. So here is the problem that they would like us to solve in the book. Limit as h goes to 0. Limit as h goes to 0 of 1 over x plus h minus 1 over x divided by h. I know, beautiful, right? So this difference quotient is just for 1 over x. Function 1 over x. You can see it here. Remember that this piece is f of x. So that's where you read what the difference quotient is for. So this is a difference quotient set up for basic function 1 over x, and we have the limit as h goes to 0. Now, because h goes to 0, we cannot plug in, because we have h in denominator, and that makes denominator 0, so we can't plug in and walk away, which means that we have to shovel the algebra here. The only thing that we can do is what in this case? It was in that list of things that I mentioned. I said rationalizing, I said factoring and canceling, and then I said another thing. Add fractions, exactly. Add fractions. So you are going to look for the common denominator for the top two fractions, and you are going to, well, subtract them. Technically, add them. So, what is the common denominator? Well, I have to multiply first one by x, and I have to multiply second one by x plus h. So, basic algebra to add two fractions. You look for common denominator. So now, the fraction on the left becomes, becomes x divided by x, and in parentheses you have x plus h. And the fraction on the right, minus, becomes x plus h divided by, and then you have same x plus h. Everything divided by h, and don't forget the limit in front, because you need to copy it every time. Limit h goes to 0, and now when you put those two fractions together, you have the common denominator of x plus h. In the numerator up there, you have x minus h. That minus distributes to both x and h, so they're both negative. And this is where you see that x cancels. So now you can add over 1 under h, so you can deal with the double fraction. So limit h goes to 0, and you multiply 1 and negative h, so that's negative h, divided by, and now you multiply. So the double fraction works this way, guys. You multiply two that are far apart, and you multiply two that are close by. That's the way the double fraction works. So 1 times negative h on top is negative h, and these two in the middle will create x plus h when you multiply the two that are close by.
Because for that, you're just multiplying
the reciprocal, right? Yes. So this is a quick visual way to do it. And now you see this h dies. There we go. And now you can actually do the limit, because what's left is the limit h goes to 0 of negative 1 divided by x plus h. When h goes to 0, right? Now you can plug in 0 for h, because it's not going to make denominator 0. When you plug in 0 for h, you get negative 1 over x squared. This is a limit problem with algebra, right? We technically did a ton of algebra. What was calculus in this problem? Know that you plug in h equals 0, right? When you can. That was calculus. Everything else we did common denominator, we shoveled the fractions, the double fraction, and right? Calculus happened from here to here to replace this h with 0, right? That was calculus. The rest of this was all pre-calculus, all algebra calculations. I hope you will practice this. This is obviously also live, so you can rewatch the video if you need to. But this skill, guys, is coming back in 2 weeks. What are we doing in 2 weeks? Definition of the derivative. And definition of the derivative, eventually we're going to repeat this problem, and we're just going to say derivative of 1 over x is negative 1 over x squared. And then someone is going to go, why? And I'm going to go, this why. Because this over here will be the definition for it. All right? So now we are not going to define derivative, we're just going to do a random limit problem, which happens to be something that we need. So, something that you'd have done in pre-calculus, maybe your teacher did not put any emphasis on these problems. As I said, maybe you don't even remember difference quotient at all because there was no emphasis. I make sure to make a big deal out of it because you are not really taking pre-calculus without taking calculus. Why would you preheat the oven and then not use it? Make sense? Right? Does it make sense? You go and you just turn it to 400 degrees and then 15 minutes later you shut it off and leave. So that's taking pre-calc and then totally not taking calculus, at least Calculus 1, So that's the idea of difference quotient. I gave you the formula, I gave you the pre-calculus spiel, which is the example that you would do in pre-calculus without having these, extra spicy fractions calculations from, algebra. So this problem is in your textbook, and it's a limit problem. We're just solving limit when denominator was 0. So those are some basic limit calculations. Now we are going to talk about limit properties. So properties of the limit, in certain cases, now this is going to be your prep for Calc 2, guys. Half of your calculus, you might have heard stories about Calc. Did anyone hear stories about Calc 2?
It's all. Yeah.
Those are the stories that, yes, that are there. Why is it awful? Well, Calculus 2 is a very tricky class because it relies heavily on your prep and your ability to do things you learned a long time ago. Half of Calculus 2, first half, is integration. Heavily depends on your ability to do Calc 1. But the second part is the one that is just, it's a massacre. And that's the one that uses limits in every problem. Now, what do we have in Calc 1? 4 or 5 sections on limits in the first 2 weeks, and we are done with limits, right? And the rest is derivatives and integrals and so on for Calc 1. And then, when you get to having limits in every single problem for the second part of Calc 2, you just spontaneously combust. So these properties that I'm going to list right now will help you for some problems to actually find the limit in Calc 2. And then Calc 2 is a heavy prerequisite for differential equations. So it goes Calc 1, Calc 2, diffq as a string of heavy prerequisite. You passing this class is completely irrelevant if you have to take the other courses. You have to know this. Otherwise, you will be sitting there learning 2 courses at the same time. There is no way, in hell, to pass Calc 2 without knowing these properties and the limits, especially section that we're going to cover later, 2.5, limits at infinity. All of the limits are limits at infinity in Calc 2. So you will need to know this. Okay, let's list these properties that are so important for our later life. They're called limit laws in the book. And generally they are properties of linearity with some other stuff added. So number 1, if you have limit as x goes to a for addition of 2 functions like this, f of x plus g of x, you are allowed to figure out each limit independently and then add their results. So if I have 2 functions, let's say I have a limit of x squared plus square root of x, right? Those are not compatible functions because one is radical, one is polynomial. So you independently find both limits and then you add those numbers, whatever the limits are. If any of those limits does not exist, then obviously, right, it ruins it for all. That's like when SJW shows up in like, place and ruins everything for everyone else. Why, you never experienced that? Oh, you did. Of course you have. Come on. They're everywhere. And they have the interesting color hair, right? So you can spot them. Like those poisonous frogs. Like they say, don't touch them. Like they have the same color hair. Anyway, go on. What?
No, I'm just saying. That's true.
Well, of course it's true. That's why I said it. 100% of what I say is true. All right. Look at these limits. Test it on any function, it's going to work. I promise. That's why I do math. All right, next one. Subtraction, same deal. If you have two functions that you cannot combine with algebra, you can get them worked out separately and then just work the numbers on the other end. So we have f of x minus the limit of g of x, so separate. And now this is going to hold next one in multiplication, division, squaring, and all of that. Before we go into multiplication, we have scalar multiplication, which is what allows you to kick the constant number in front of the limit and not worry about it. So if you have limit x goes to a of c, some constant, let's say 7, times f of x, you can kick that c outside, do the limit for f of x, right? And then multiply by that number. This property, so these three properties will be there for derivatives and integrals the same. Now, we have the property that only works for limits. Derivatives and integrals will have special rules for these. So limit of f of x times g of x is equal to the limit of f of x times the limit of g of x. Now you probably go, yeah, what's so special about it? I just solved both of them separately and multiplied the answers. Yes, nothing special about it, but it only works for limits. Derivatives and integrals will have special formulas for this. So these rules are only exclusive to limits. Now we'll do the division, the same, f divided by g. And you are dividing the limits. So it would be the limit of f. Now I'm starting abbreviating because I got, it's just too many parentheses. Squaring, not just squaring, any exponent, which also includes the roots and stuff, because roots, what's a square root? It's a half exponent, right? What's the fourth root? 1/4 exponent. So roots or exponents, they all go on a pile over here, saying that the limit of f raised to some exponent n, I don't care if that exponent is number or a fraction, either way, you are allowed to take the limit of f of x as x goes to a and then apply that same exponent, whether it's a square root or what do you call it? Square root or a cube or whatever exponent you have. So these are your limit laws. And we don't really have any, spicy examples where we get to use these. They will be there in Calc 2. I accidentally chose a problem for exam which had this rule in it, and it was a massacre. So I have to be careful too, right? So you are going to see right now in Calc 1, we just do some basic stuff, more like, mathematical gymnastics. Let's see. Say you have limit as x goes to 3 of this unknown function f of x is, let's say, 6. And the limit x goes to 3 for g of x is, let's say, 1/2. And then the limit of x goes to 3 for some function h of x is what number? Can't think of any number. 8 it is, thank you very much. 8. So now I am asking you, what is the limit as x goes to 3 for 4f of x minus g of x squared. Oh, it's terrible. Whatever. No, let's put h of x. H of x squared divided by g of x. Like that. Limit laws allow you to assign limit to each function and then deal with algebra and order of operations. So that's the key. So using the limit laws, you are able to say for limit x goes to 3 of f of x minus, open parenthesis, limit of h of x everything squared as x goes to 3 divided by limit of g of x. And then you just replace every limit by the value you had. You can do it, come on. There you go. So I have a block over here, and that block gets replaced by 6. So I just get 4 times 6 minus 8, who picked 8? Divided by 1/2. And then you just calculate this. 6 times 4 is 24, minus 8 squared is 64, divided by 1/2. This is going to be negative 40, divided by 1/2 equals negative 80. And the limit is negative 80. You can see that I replaced the whole block of f of x with 6. I replaced the block of limit of h with 8, and then replaced limit of g with 1/2, and just carried the arithmetic to compute. So these rules allow us to deal with these things, allow us to split the limits when we need to split them. We are going to use some of these rules to prove the derivative. This is going to shine in your Calc2 class, right? And then if you don't know these things, obviously you have to relearn all of that stuff in Calc2, which actually makes Calc2 difficult because you are taking Calc1 and Calc2 at the same time. Then you add trig to it, because you have trig integrals and trigonometric substitution and other stuff, right? It gets really spicy if you don't remember those things. Okay. I think this seems to be working. Is this working? The selected projector is busy. Do you want to connect? Yes, I want to continue. Let's see. Now we get to the last part of this lecture, which is this one part that you pretty much don't get to see that often. It's called the squeeze theorem, also known as the sandwich theorem. It's to find the limit of some cases where the methods that we did so far don't really fit and work. Obviously, the chart method works all the time. The question is just, do you want to sit there and compute? So let's take a look at the end of the section, which is the squeeze theorem. And the squeeze theorem is going to ask you to create two functions that are going to sandwich the function of interest in between. So let's say, this is pretty much the same example as the book. You have some function that goes like that. and you would like to know the limit at 0. Now, what you see over here is a lot of oscillation. And you don't really know what is happening at 0, right? So what you do is you create a function that is higher and then a function that is lower, like that. And then you find the limits of the red and blue function. And if the limit of the red and the limit of the blue function is the same, then the function that is sandwiched in between has to have the same limit. Which is why they call it a sandwich theorem, squeeze theorem, but also the sandwich theorem, depending which book you read. What do you have for sandwich? Bread, some cheese. If you're lactose intolerant, put 2 slices. And then another piece of bread on top, right? Now, you're interested in cheese, not the bread, right? But when you grab the sandwich, you grab the bread. Whatever you take the sandwich, the cheese goes with it because it's squeezed inside. So, you are creating a function that is going to sandwich in the function you care about, and then by computing these two, the one that is sandwiched in between has to be at the same spot. Because when you take the sandwich, right, the cheese is stuck inside and it has to go with the sandwich, wherever you take the sandwich. So, let's take a look at the example of this. I believe you might have a single homework assignment, like problem on this. I believe it will show up maybe once or twice in your lifetime of calculus. So we talk about it and then we move on with our lives. Let's see the example here. It's beautiful, epic. Look at this. Limit x goes to 0 of x squared times sine of 1 over x. It's amazing. Look at that. Can you plug in 0? No. What, the sine wants to explode, right? Because you have sine of the... Now, there are analytical tricks. If you are good with mathematics and you understand mathematics from the point of view of a form, not examples, you immediately know that sine can at most be 1, right? Because the range of sine is from -1 to 1. So you can never get a number larger than 1 for this. And because of that, you can just throw it in the garbage. And then the limit of x squared is 0 is 0, and you're done, right? But if we are not making that argument, okay, we can use what we call the squeeze theorem. So you start by saying that sine x is bounded by 1. Now, this is a fancy way to write the range of the sine function. And then in algebra, you learn that that's written as, I don't need red anymore. In algebra, you learn that that's written this way. And we don't care what's here. So we can just put 1 over x if we want to. So this is where you start the problem. You say sine of 1 over x, leave some space right there. So sine 1 over x is stuck between -1 and 1. And now when you are comparing these, you see that you have x squared missing. So what you do is you multiply x squared, so times x squared, times x squared, times x squared. You multiply through by x squared, and you get negative x squared less equal than x squared sine 1 over x less or equal than x squared. Now you see that the function you care about, and it's tough because it has this sine 1 over x term, function you care about is sandwiched between the two easy functions, right? So what you do is you take the limit of negative x squared as x goes to 0, and you get the big fat 0, and you take the limit as x goes to 0 of x squared, which also gives you 0. So what happens with the thing that is sandwiched in between? Must be 0, right? So these two together will make limit of x squared sine of 1 over x to also be 0, because it's sandwiched in between, squeezed in between. So depending on which book you read, depending on which video you look up online, they might call it sandwich theorem, they might call it a squeeze theorem. Your book is calling it a squeeze theorem. And all we did is we squeezed the function we care about between the two functions that help us figure out the limit. And that's 2.3. Techniques in computing limits. One more time. We learned, on Tuesday, we learned last class that we have graph and chart as options. Today, we said plug in if the denominator is not 0. If the denominator is 0, we must use algebra. Algebra has all of the different values, all of the different methods we discovered, rationalizing, factoring, adding fractions, all of the little tricks. And then we ended with what we call the squeeze theorem. Now we're going to take a short break, about 300 seconds or so. And then when we come back, take a look at infinite limits. 2.4.